Assalamualaikum warahmatullahi wabarakatuh. Good morning, selamat pagi. Terima kasih sudah bergabung ya untuk kelas hari ini. Nah, ini kode untuk S2 ya. Jadi kode untuk S2 kodenya adalah 839213. Yeah, this is the code for master students. Yeah, the code is 839213. Nah, untuk S3 ya, for PhD students, the code is 757684 for doctoral student. Okay, and for the grouping, yeah, for the grouping, for the project, yeah. So I have divide the class into two groups. Yeah, I want to divide the class into 18 groups. Yeah. 18 groups of 2 members for each group. Yeah, so there will be 2 members for each group, and this is the group. Ya, jadi ini pembagian ya, pembagian kelompok untuk project ya. Yang mana di situ kita ada total 37 orang ya. Nah, kemudian dibagi menjadi 18 grup ya, di mana setiap grup terdiri dari 2 orang. Ya, jadi nanti ada 18 grup ya. Nah, ini kemudian ada satu ini yang namanya Blengoh Beni Wijaya. Ini saya kurang tahu, mungkin ada yang kenal ya? Tidak ada. Karena ini sejak awal sepertinya tidak aktif ya. Jadi sejak awal juga tidak pernah mengumpulkan tugas maupun hadir di perkuliahan. Jadi mungkin tidak aktif ya Blengoh ini. Ini nanti jadi total hanya 36 yang saya bagi menjadi 18 grup. Jadi ini nama-namanya ya. Jadi nanti bisa mengkontak temannya dalam satu kelompok ya. So this is the group. We have 18 groups here ya. We have 18 groups in which each group will have 2 members ya, 2 members. And here yeah, so you can contact your the other group member, yeah, your partner, yeah, in the group, so that you can prepare for the project. Yeah. And to catch up with the material for the project, so today we will discuss about partial differential equations. So last week we have learned about ordinary differential equations, ODE. Yeah, in which we have discussed about the initial value problem and the boundary value problem. And we have another problem, which is the eigenvalue problem, in which I will hold that for now. Yeah, so we will back to discuss about eigenvalue problem later when we have discussed the partial differential equations, because we need to catch up with the material for the project so that you have more time to prepare for the project. Yeah, so that we will hold the eigenvalue problem for the moment. Yeah, so we will continue on the next chapter. Later we will return to eigenvalue problem, yeah, at the end of the course, because what we are going to have in the project is related to the partial differential equations. Okay, and this grouping has been uploaded in classroom as well, so you can check that again. Yeah, and you can contact your partner. Yeah, I think you can probably you have known the other group member before, or if not, you can contact through finding the contact through, I think you have groups as well, yeah, for postgraduate students, or you can find it in our group, in WhatsApp group, yeah, for the contact for each of the member. Okay, so this is the grouping. Any questions for the grouping?
No, ma'am.
Okay. All right, so that I think that's clear. Yeah, so you have known your partner, and again, if you haven't do the presentation online, so this is the code for postgraduate students. Yeah, so 839213, and this is for doctoral students 757684. Okay, so now we will continue on the discussion on partial differential equations. Yeah. So I will share the slide now. Okay, so part 8, yeah, so this is included in part 8 in the book, is about the partial differential equations. And this is particularly important, yeah. We have many application of this when we have an equation we have an equations, for example, in which it will have a dependency to two independent variable. Yeah. So what are the cases? So we can see here, for example, we have heat conduction on two-dimensional plate or even three-dimensional body. Yeah. So if, for example, we have a plate here and we want to we hold the top side and the left side hot and the bottom and the right side cool, so that we will have heat distributions, the temperature distributions uh, on the plate. Yeah, so that if you want to find the temperature here for each of the locations on the plate, so that will depends on two variable, the x coordinate and also y coordinate. So when we change the one of the independent variable, so that the temperature will change as well. So that means the temperature is a function of x and y. Yeah. In here we have a spatial direction, which is in x and y direction. And also, if we have another problem here, for example, we have a two dam, and this dam has a as a base of impermeable rock, so that there can be a flow that is absorbed and then directly to the lower head, to the reservoir with lower head, so that we see here that we can have a flow line of the liquid of the water through the impermeable rock, so that if we want to find, for example, the velocity, yeah, or the mass flow rate, for example, inside the impermeable rock, so that will depends on x and y direction as well. So if we have different locations, so that we have different flow line, it means that the flow rate is also different as well. Yeah, and also if we have, for example, a magnetic field here, we have a conductor, for example, and here we have a different electromagnetic field. Depends on the strength of the magnetic field, will depends on the position of x and y. Yeah, so that we see here that many applications based on partial differential equations. And this is how we write down the partial differential equations. Yeah. So that if we have a function, yeah, f function here, yeah, a function. So this function will depends on at least two, yeah, or more independent variables. So for example, we can write it down as x and y. So that means this function is dependent on x and also y variable. Uh, Depends on x and y variable. Well, what we have in ODE before, if we have ODE, so that we have a function which is only depends on one variable. So for example, it depends only on x. So y as a function of x. While if we have ODE, yeah, or we can write it down, for example, dy dx here is only a function of x and y, for example, in which y it depends on x. While here we have a function which depends on two variables, which is x and y. So that we have several types of PDE. The first one is called the Laplace equations, in which for Laplace equations we have this form. Yeah, so we have the second derivatives of functions in x direction plus the second derivatives of the functions in y directions, that will be equals to 0. So this is called the Laplace equations. The second group for the PDE is called the diffusion equations. Yeah, so this is relates to the diffusion or also, yeah, conduction. Yeah, so we have here diffusion equation is K, which is a diffusion coefficient K, times the second derivatives of f in x directions. So that will be equals to the derivatives of f in t. Yeah, the derivative of f in t. So that we have here that, for example, here we have function which is dependent on x and y, while the second one we have a function which depends on two variable, which is x and t. Yeah. And the third one is the wave equations, in which we have the second derivatives of y in x directions, and that will be equals to 1 over square c times uh, the second derivatives of y and in t direction. So that we also have here that the function will depend on two independent variable, which is x and t. Nah, jadi ada tiga penggolongan di sini ya, tiga kelompok PDE. Ya, ada tiga kelompok PDE yang mana nanti akan kita bahas satu persatu ya. Yang pertama adalah Laplace ya. Jadi nanti apa perbedaan dari ketiganya ini, nanti sebetulnya punya karakteristik masing-masing. Ya, ada perbedaan dari ketiga grup ini, ya, yang mana nanti karakteristiknya juga akan berbeda. Ketiganya merupakan PDE, jadi di situ ada derivatif ya, karena namanya diferensial berarti ada fungsi derivatif di situ, ada term derivatif, yang mana fungsi itu merupakan fungsi yang tergantung ya pada dua independen parameter. Ya, dua parameter independen. Masing-masing ini bisa kita lihat kalau di sini f sebagai fungsi x dan y, maka diturunkan terhadap turunan kedua terhadap x dan y. Kalau difusi, persamaan difusi di sini ya kita punya turunan kedua terhadap x dan turunan pertama terhadap t. Jadi merupakan fungsinya merupakan fungsi dari x dan t. Wave equation juga demikian ya. Nah, ini nanti dari ketiga ini nanti punya karakteristik yang berbeda. Nah, nanti akan kita pelajari ya. Jadi di sini kita lihat bahwa ada klasifikasi ya. Jadi ada klasifikasi dari PDE, dan ini menjadi sesuatu yang penting untuk kita paham ya. Masuk di mana ya kasus itu, apakah tergolong Laplace diffusion atau wave equation. Karena nanti karakteristiknya akan berbeda. Ya. Nah, ini kaitannya kalau kita perhatikan semuanya ini dalam penggolongan ini adalah linear second order. Artinya second order, kalau kita punya second order ODE, artinya di situ ada turunan kedua. Ya, jadi semuanya ini kalau kita lihat dari klasifikasi ini seluruhnya adalah second order PDE, ya, second order PDE yang mana linear. Dan ini kategori ini terkait dengan problem-problem yang kita temui dalam engineering, ya, dalam bidang kita. Dan mengapa kita harus memahami? Karena nanti penyelesaiannya berbeda, walaupun basisnya sama ya. Nanti penyelesaiannya akan sedikit berbeda, ya. Beberapa metode nanti akan sedikit berbeda yang dikembangkan, ya. Nah nanti, ya, sehingga nanti kita akan selain metodenya berbeda, juga nanti pengaruhnya dari independent variable terhadap fungsi itu juga akan berbeda. Yeah. So it's important to us to understand these classifications because we will have different approach, and also as the implications that this classification will also have different characteristic, yeah, of the independent variable to the function. So that if we see here, for example, we have a general form of PDE. Yeah, if we have a general form of PDE in which we have second order linear PDE, which two independent variables, so we can write down the general form as this one. So that if we have this UXX as a subscript here, I think, I hope you still remember that this is in mathematics. Yeah, so that we can also write it down the general form as A, the coefficients times del squared u over dx squared. So this is the means that uxx is the second derivatives in x direction. Yeah, so that if we have p u x y, so that means we have p, that means we have del, yeah, del x, del u, del y, yeah, so that we have del yeah. So that we can write it down as del y del u over del x. So that if we have u x y, it means that we have the first derivatives in x and then we find the derivatives in y. Yeah. Plus if we have c u y y, so that means we have del squared u over del y squared plus t, that will be equals to 0. So that this is the general form of PDE, linear second order PDE, so that we can find to match this what we have before. So if we have Laplace equations, so that here we have a functions, the derivatives of a function to x and y. Yeah, so that we have here, so the Laplace is actually, if we write down the Laplace equation, so that will be del squared u over del x squared plus del squared u over del y squared, that will be equals to 0. So if we look at the general form here, so this is a, yeah, so this is a equals to 1, yeah, and c here, so this is the coefficient of c is equals to 1. Yeah, so that if we write it down here, so we have a and c, so that we can do the classifications by finding the value of b squared minus 4ac. Yeah. So if we insert the value here and we found that this value is lower than 0 or negative, it means that we have an elliptic equations. Yeah. So this is called the elliptic PDEs. if we have b squared minus 4ac is equal to 0, so that means we have a parabolic PDE. If we have b squared minus 4ac greater than 0, it means that we have a parabolic equations. So that for the first here, we have Laplace equations. Yeah. So that this means that we have a equals to 1 and c equals to 1 as this one. So that we have b squared minus 4ac lower than 0. So that we have the first group here, the first classification for Laplace equation is an elliptic equations. So what is the example here? For example, we have a function of u which is equals to e to the power of x times sinus y. So that we have a function u which is depends on x and y. So that here we have the first derivatives of u in x directions, which is e to the power of x times sinus y. The second derivatives is also the same, e to the power of x times sinus y. Well, if we find the first derivatives of u in y directions, so that we have e to the power of x times that we have, we find the first derivative, so that will be cosinus y. Again, the derivatives of cosinus y will be minus sinus y. So that if we do the addition, so that will be equals to 0. So this is one of the example in which we have an elliptic equations. Yeah. So this is the first class, which is an elliptic equations. Ya. Jadi persamaan pertama adalah Laplace ya. Persamaan Laplace ini adalah persamaan eh, eliptik. Ya, persamaan eliptik. Karena kalau kita masukkan di sini tadi ya, kita cocokkan tadi nilainya, bentuk umumnya, berarti yang ada hanya term pertama dan term ketiga. Jadi B-nya 0, D-nya juga 0. Sehingga A1, C1 ternyata ketemunya adalah lebih kecil dari 0, jadi masuk eliptik. Ya, itu yang pertama. Now we will look at the second example in which we have the heat equations. Yeah, that we have the heat equations. For example, we have unsteady heat conduction. Yeah, unsteady heat conduction. So here we have, for example, the conduction coefficient is alpha. For example, alpha times del. The second derivatives of u in x directions minus del u over del t. So the first derivatives in time, and that will be equals to 0. So with these equations, we have A, which is equals to alpha, and B, yeah. So that do we have B? We don't have B value because we have the derivatives in X and Y. So we don't have B value. And also C value, we don't have C value. Yeah. So that we don't have C value. Uh, so that this will be D, yeah. So we don't have C value. So B squared minus 4AC will be equals to 0. So that equation, this equation is called the parabolic equations. Yeah. So that the last, which is the wave equation. Yeah, we have wave equation here in which we have the coefficient of c squared times the second derivatives of u in x direction minus the second derivatives of u in t directions, and that will be equal to 0. So we will look at this equation so that we have the second derivatives here. So this is this is will be a, yeah, and this one minus 1 here will be c, yeah. So that the b value is 0, so that if we insert the value b squared minus 4ac, so that we have c is minus, so that will be positive, so that will be greater than 0. So this is included in hyperbolic equations. So we have 3 examples here in which 3 equation is classified as different PDE. Yeah. And how we will look at the characteristics. So if we see here, for example, we have an elliptic equations in which we have, for example, two variable, which is x and y. And for each of the coordinate in x and y, we have a different value of u. So u as a function of x and y. So we see here if, for example, there is a little bit of disturbance here. So a value, for example, here is changing. Yeah. So that means that a disturbance at one point, or the value that changes at one point, will have effect to all of the area that is in the domain of calculations. So it means that if we have an elliptic equations, it means that if we give one disturbance, one point in the domain, we give disturbance of different value at one point, so that will have effect on all of the calculation in the domain. Yeah, so that will have effect on other points inside the domain of the calculation of x and y. So this is called the elliptic equation. So the characteristic is when we have disturbance at one point, it will have effect in all area in the domain of calculation. Now the second one, we have a parabolic equation. So what is the characteristic for a parabolic equations is that, for example, here we have two independent variable, which is x and t. So here we have x and t, and we have the dependent parameter, which is u. So that what happens here, if, for example, we have a disturbance at point P here at a certain X value and T value. So what happens here? So that this disturbance will have effect on the subsequent time, but it will have no effect on the previous time. So that we see here that we can divide the domain of calculations of domain of dependence, in which this will also have contributions to the effect of what happens after. Yeah, so that we have the lower part here is domain of dependence, so that this will have effect to the subsequent time step, while on the top side we have domain of influence. So it means that if we have disturbance at one point here, so the domain after, yeah, so if we want to calculate up the subsequent time step, so that will depends on the disturbance at point P, and also to another another points inside the domain of dependence. So this is the characteristic of the parabolic equations. While if we have a third classification, which is a hyperbolic equation, so that means if we have a disturbance at point P here, yeah, and we have, for example, here two independent variable similar to in parabolic equation before, so that we can write down the plane here, the xt plane. Yeah, we have the xt plane, so that if we have the disturbance at point P here, for example, so what will affected by what area will be affected by this disturbance, we will have the domain of influence here, which is not along the area, not in all area of the domain of calculation, but only in narrow area closest to point P. Yeah, and also the domain of dependence is not depends on all area as in the parabolic equations, but here if we have hyperbolic equation, it means that the domain of dependence becomes narrower as well. So this is the characteristic of an hyperbolic equations. Ya. Jadi ada tiga penggolongan di sini ya, di mana ini tidak hanya sekedar persamaan saja ya, tetapi ada pemahaman fisis sebetulnya dari persamaan yang sudah dibuat. Ya, jadi masing-masing punya sifat, punya karakter ya. Jadi coba kita bahas kembali lagi ke yang pertama, yaitu eliptik. Yang mana kalau kita punya semacam ini, maka U ini merupakan fungsi dari X dan Y. Ya, maka kita gambarkan coba di sini. Ya, ini sebetulnya tiga dimensi ya. Jadi pada bidang X dan Y, maka nanti ada nilai U, di mana nilai U tergantung pada lokasinya di tiap-tiap titik. Nah, artinya katakanlah kita punya domain komputasi itu seluas ini, ya. Maka kalau kita punya persamaan eliptik, katakanlah, dan saya berikan disturbance atau gangguan atau suatu nilai yang berubah, ya, suatu nilai yang berubah di titik P ini katakanlah, maka apa akibat P terhadap domain komputasi yang kita selesaikan, maka titik P ini akan berpengaruh ke semua titik. Contohnya, misalkan temperatur, ya temperatur. Tiba-tiba di tengah ini saya panasi dengan temperaturnya naik. Maka bagaimana pengaruhnya? Maka semua titik ini akan terpengaruh oleh titik P ini. Ya, artinya nilai-nilai di semua titik ini di dalam domain ini akan berubah juga ketika nilai P ini dirubah. Nah itu, ya artinya apa? Dependensinya satu titik dirubah, semuanya akan berubah. Ya, itu untuk sifat dari persamaan eliptik. Kalau kita punya persamaan parabolik, ya, yang mana ini ditunjukkan oleh persamaan semacam ini, kita punya misalkan U itu sebagai fungsi dari X dan T. Ya, di mana di sini kita punya bidang X dan T, di situ ya, kita punya bidang X dan T. Nah, kemudian kemudian kita akan memberikan suatu gangguan, disturbance, atau kita ganti nilainya di satu titik tertentu. Maka ketika kita ubah nilai di satu titik tertentu, ini mana yang akan berubah? Ya, kalau kita ubah satu titik, maka tidak semuanya berubah, ya. Hanya pada time step sesudahnya. Dalam hal ini T. Ya. Jadi hanya berubah ke atas saja. Kalau ke bawahnya tidak berubah. Karena apa? Kalau kita bicara tentang waktu ya, secara fisik, artinya kalau ada gangguan, maka yang mengalami pengaruh itu adalah sesudahnya. Apa yang terjadi sebelumnya tidak akan terpengaruh. Ya, sehingga ini adalah sifat dari parabolic equation. Sehingga apa yang terjadi kalau ada gangguan, maka yang mengalami perubahan, ya, yang mengalami dampak dari perubahan itu hanya pada time step sesudahnya. Sebelumnya tidak terpengaruh ya, tetapi ini disebut sebagai domain of dependence. Artinya apa? Artinya nilai yang ada di atas ini ya akan terpengaruh oleh P, gangguan yang diberikan di P, dan apa properties yang dimiliki sebelumnya, seperti itu. Jadi katakanlah saya ingin cari di sini, ini akan terpengaruh juga dari P di sini, tetapi dia juga akan terpengaruh oleh apa yang terjadi sebelumnya di titik yang sama, seperti itu. Jadi ada yang namanya domain dependence dan ada domain of influence. Jadi tidak semuanya berubah, ya, seperti itu. Yang terakhir adalah hyperbolic equation. Kalau hyperbolic equation ini sama ya, suatu persamaan yang merupakan fungsi X dan T. Ya, jadi kita buat juga plane-nya X dan T. Nah, bedanya apa? Ya, bedanya kalau kita berikan disturbance di satu titik P, ya, kalau kita berikan disturbance di satu titik P di situ, maka disturbance ini akan mempengaruhi, ya sebentar ya. Ya, kita kembali kemari ya. Jadi kalau kita punya persamaan hiperbolik, maka adanya gangguan pada titik P di situ, ini hanya mempengaruhi daerah yang kecil saja, daerah yang dekat dengan disturbance itu. Jadi tidak seluruh area seperti yang terjadi pada persamaan parabolik ya. Jadi hanya memiliki dampak pada daerah yang memang dekat dengan P. Daerah yang jauh dengan P bagaimana? Ini tidak ada masalah. Jadi tidak ada pengaruhnya. Kita berikan gangguan di sini, ini tidak sampai mempengaruhi oleh daerah yang jauh dari titik P. Ya, di mana daerah yang dekat dengan titik P ini yang hanya yang terpengaruh. Dan ini ada domain influence dan juga ada domain dependence. Berarti apa yang terjadi di sini juga dipengaruhi dengan apa yang terjadi di titik P maupun yang sebelumnya terjadi ya. Jadi ada domain of dependence. Tapi hanya melingkupi daerah yang cukup dekat dengan P saja. Yang jauh tidak terpengaruh ya. Jadi kita perhatikan di sini yang jauh tidak terpengaruh. Jadi ini ciri-cirinya ya, karakteristiknya dari ketiga persamaan tersebut. Jadi secara fisik pun berbeda artinya ya. Nah, jadi itu pengertiannya dan ini perlu dipahami ya. Jadi tidak sekedar kita menyelesaikan ya bagaimana metodenya, tetapi paham secara fisik. Dan ini nanti akan aplikasikan. Ya. Jadi kita lihat contoh yang pertama ya mengenai PDE yang terkait dengan persamaan panas heat equation ya. Jadi persamaan konduksi unsteady di sini ya. Unsteady conduction, unsteady one dimensional conduction ya. Jadi kita punya heat equation di sini ya yang mana alfa del kuadrat U per dx kuadrat dikurangi dengan del U per dt sama dengan 0 ya. Jadi kita lihat di sini ada apa? U atau di sini U itu dapat kita gantikan sebagai temperatur, maka temperatur itu tergantung pada posisi X dan tergantung pada waktunya. Jadi kalau kita misalkan gambar ini sebagai 1D conduction ya, misalkan semacam ini mirip dengan kemarin ya, kita punya 1D conduction. Ya, tetapi bedanya sekarang, jadi ini misalkan kita tahan 100 derajat, yang di sini kita tahan 40 derajat Celcius. Tetapi bedanya sekarang unsteady. Ya, jadi ada perubahan terhadap waktu. Ya. Jadi misalkan misalkan saya punya ini temperaturnya mula-mula adalah 200 derajat misalkan ya, rata 200 derajat atau semuanya rata 0 derajat. Maka bagaimana pengaruhnya? Kalau katakanlah ini semuanya adalah 0 derajat begitu ya. Bagaimana pengaruhnya dari waktu ke waktu sehingga memenuhi dari 100 sampai 40 derajat di sisi kiri dan kanannya. Seperti itu. Jadi ada selain ada pengaruh ke arah X ya, kalau ini katakanlah ini adalah ke arah X, tapi juga ada pengaruh ke arah waktu. Ya, ke arah waktu. Artinya dari waktu ke waktu, awalnya temperaturnya konstan ya. Misalnya ini di boundary 100, kemudian langsung berikutnya seperti ini. Nah, nanti dari waktu ke waktu kita lihat untuk T0, kemudian T1 ya ini mulai ada perubahan, mulai misalkan semacam ini ya. Nanti T2 sudah mulai nanti lama-lama menjadi linier semacam itu. Nah, ini contohnya adalah heat conduction ya, unsteady heat conduction. Sehingga kalau kita punya persamaan ini, maka juga dibutuhkan boundary condition. Kalau ada dua variabel, maka harus diberikan ya. Jadi kalau kita lihat PDE yang di sini ini merupakan gabungan antara apa? Initial value problem dan boundary value problem dari ODE. Ya. Jadi kita aplikasikan di sini ada boundary conditionnya. Yang pertama yaitu pada U0 yaitu sisi kiri berapa? Di sini diambil 0. Pada sisi kanan yaitu U1T berarti pada setiap waktu apa saja waktunya itu ditahan tetap ya, yaitu 0 juga. Berarti ini adalah boundary value-nya. Sedangkan untuk initial value diambil untuk T sama dengan 0 ya. Jadi untuk T sama dengan 0 pada semua nilai di sini ya, maka sama dengan sinus Px. Jadi merupakan suatu fungsi ya pada initial value-nya. Baru nanti akan berubah. Ya. So we will look here one example which is the heat conduction heat equation. Yeah. So we see here this is unsteady one-dimensional conduction. Yeah. So that we can, for example, solve this equation for 1D rod, for example, to find the temperature distribution, but the temperature distribution is not steady. So this is unsteady. It means that it can change with time. Yeah, for the temperature distribution along the rod. So to solve for this equation, we need a boundary value problem here. So we need to define the boundary for x equals to 0 and also for x equals to 1. So on the left and on the right side. So this is a boundary value problem, as well as we need to insert the initial value for t equals to 0. So this will be initial value problem. So we define the temperature, which is U here. Yeah, so U at X, which is a free variable. So it means that along X-axis here at T equals to 0, yeah, at initial state. So that will be as a function of sinus pi x. So it means that it will have a sinus pi x distribution initially. And then we can calculate along the time, yeah, so that we can find the distribution with time. So that is one example relates to heat equations. So that we will discuss on the solution method for these PDEs. Yeah. So that how to solve for PDEs, we can have analytic solution, but this analytic solution is only available, only feasible to be performed in simple and special or ideal cases only. So that we will use the method that we have discussed in ODE as well, which is the finite difference technique. So this is very similar to what we have learned last week, yeah. But now we will extend it in for the dependency to more than one variable. Yeah. So this is what we are going to discuss today. Yeah. So the first one is finite difference methods. So that we have a similar procedure to ODE in which we will use the central divided difference to substitute for the derivative which is appear in the PDE. So that we will transform, yeah, we will transform the PDE into a set of algebraic equations, and that we can solve it when we have a set of simultaneous algebraic equations. We can have a matrix form, yeah, so that we can solve it using the method that we have learned before. We can use Gaussian elimination, or we can use Gauss-Seidel or other iterative method. So this is the example, yeah, of the central divided difference. Yeah, so we will return on here, yeah, in which we have central divided difference. We can apply it for two-dimension case here, in which we can use it to solve for uh, of a PDE, yeah, of a function which depends on x and y direction. Yeah. So that if we want to find the first derivative in x directions, so here, for example, we want to find the gradient at point ij, so we can approximate the gradient here, yeah, with fi plus 1j on the right minus the point on the left, yeah, so the point on the right minus the point on the left over the distance, which is 2 delta x. So we assume here to have a uniform spacing, yes, to have a uniform grid spacing, so that the distance from I plus 1 to I minus 1 will be 2 times delta x. And if we want to find the second derivatives, yeah, so this will be a second order, yeah, second order accurate. And if we want to find the second derivative, second order accurate as well, so that we can find the second derivatives at this point, that will be approximated by fi plus 1j minus 2 fij plus fi minus 1 on the left j over square delta x. I think we have learned this before. So this is just a review. We learned that on numerical differentiation. Yeah. And also, if we want to find the gradient in y direction, because this is two-dimensional. If we want to find d del f over del y, so this is the gradient in y direction, so that with central divided difference, so that will be Fij plus 1, so the node at the grid at the top, minus Fij minus 1, so the grid at the bottom, over 2 times delta y. So that is the distance between j plus 1 and j minus 1. And if we want to find the second derivatives, yeah, so that will be similar as in x direction. Yeah, so that will be Fij plus 1 minus 2 Fij plus Fij minus 1 over square delta y. Yeah, so that if we have these definitions that we have before with the central divided difference, we can substitute this one to the equations that appear here. Yeah, so if we need to find the second derivative in x, so that we can substitute it with this value. And again, if we need the derivatives in y direction, so we can substitute with this value as well. So that now we will apply the finite difference method to the elliptic equations that we have discussed before. Yeah. So here we will discuss about elliptic equation, in which we have the elliptic or Laplace equation. Yeah, so this is called an elliptic or Laplace equation, one of the example of elliptic equations, in which this is appear commonly in engineering problems. For example, we have steady state distribution. So steady state distribution of a heat in a body. So heat in a body means that it can be two-dimension body or plate or three-dimensional body. So that we can write it down as for 2D, yeah, for the 2D case, we can have the second derivatives of temperature in x direction plus the second derivatives of temperature in y direction, so that will be equals to a function. Yeah. Or we can also expand that in 3 dimensions. For example, if we have 3-dimensional bodies, so that we can write it down as the second derivatives in x direction plus the second derivatives in y direction plus the second derivatives in z direction. So that will be a function of x, y, and z, for example, in 3 dimensions. But now we will focus on 2 dimension first, yeah, because yeah, we will focus on this, yeah, so that if we have T is the temperature at point X and Y, yeah, so that if we have a domain here, so that T will be a temperature at a point inside the domain, yeah, in the domain, so that we need to discretize the domain, for example here with finite difference method, yeah, so that we can find the distribution here by making grids, yeah, on the domain that we solve in x and y direction here, in which we have fxy here is the right hand side. So the right hand side here can be a heat source, yeah, it can be positive, or it can be a heat sink or negative, yeah, so it can be absorbing or producing heat, yeah. Okay, so that is the equation. So this is included in elliptic equations. Yeah. Okay, if we have no heat source available, so that we can cross the system on the right side, so that we have d squared t, or the second gradient, the second derivative of t in x direction plus the second derivative of t in y directions, that will be equals to 0. Yeah, when we have no heat source. Okay, so that we will see here how to discretize uh, the domain. Yeah, so say we have a domain of a plate here, and we can assume that this will be a two-dimensional plate. We have x and y direction here, so that we will take one element here. We will take one point here, in which this will have a length of a delta x, and the height is delta y. Yeah, and that we have a heat, the flux here on the left, yeah, is q not the flux, the value here on the left is qx, and the value on the right is qx plus delta x, and also at the bottom we have a value of q, which is y, and on the top we have qy plus delta y. So this is a function q, yeah, a dependent variable of q. So q will depend on x and also y. So that we will discretize the domain into points. Yeah, so here we are making the grid points, and we will give a name for each of the point here. So that the first point here appear on the left side, left bottom here, is denoted with 0, 0. It means that I in x direction, it will have a 0 notation, and also in y direction, this is we have a notation of 0 coordinate. So this is 0 comma 0, and then we have 1 comma 0, 2 comma 0, yeah, and so on. Yeah, so that is the I index. So this is the I index, and this is J index. So that this is the indexing of the grid points. So that X here will be the indexing of I, and Y direction here, or the vertical direction, will be the indexing of J. So that here we have 1 comma 0, 2 comma 0, 2, 3 comma 0, and so on up to m plus 1 comma 0. The number of point in x direction, the number of grid point in x direction. Well, if we have in vertical direction there in y direction, so that we have 0 comma 1, 0 comma 2, and so on, yeah, up to 0 and plus 1. So that if we have a point here, so this point will have a notation of I comma j, so that the point on the left point here will be I minus 1 j at the same y position, so same j value. On the right side, we have I plus 1 comma j. On the top, we have I, the same I value here. Yeah, I value the same. So I comma j plus 1. On the bottom here, we have I j minus 1. So that we can say that this point will depends on the adjacent point, yeah, on the neighboring points. Yeah. So that we will now substitute the central divided difference into the Laplace equation. So this is the Laplace equation. So the source term here will be equals to 0. When we have that, right hand side is equals to 0. So this is called Laplace equations. So that we substitute the second derivatives that we have here with the central divided difference, the second derivative central divided scheme, yeah, with second order accurate, yeah, which is second order accurate. So that we have here this value. So the second derivative of t in x direction will be ti plus 1 comma j minus ti at j plus ti minus 1 at j over squared delta x. Again, similar to delta y, so that we can substitute here, yeah, we can substitute it there to the equation, so that we have ti for the second derivative of t in x direction, so that will be here, yeah, and also the second derivative of t in y direction will be substituted with this value. And if we assume that delta x is equals to delta y, so that we have exactly a square grids here, yeah, we have a square grids. So delta x equals to delta y, yeah, so that we can collect together. So this can be omitted because it's the same value. So that we combine together the same value. So we have here same value together. So that we have ti plus 1j plus ti minus 1j plus tij plus 1 plus tij minus 1. We collect together this one, so that will be minus 4 tij, which is equals to 0. So this is a linear equation. Yeah. So this is a linear equations that we have that we apply to one point in here. So it means that if we want to find the value at Tij, so that will depends on Ti plus 1, Ti minus 1, Tj plus 1, and Tj minus 1. So if we want to find a value here, yeah, so that will depends on the neighboring points. So if we have one point is changing here, it means that this will have effect on this one as well, because this depends on the value of the adjacent cell. And that if we have this point changing, so that means the top, the right, and the bottom will change as well. So all the neighboring points will change, so that we can see the characteristic of the elliptical equation is that if we have one value changing at the in the domain, so all of the value in the domain will be changed. Oke. Ya, jadi kita lihat bagaimana mengaplikasikan uh, finite difference ya untuk persamaan Laplace ya. Jadi tinggal kita substitusikan saja ya. Ini tadi kita sudah punya persamaan kemarin ya untuk central divided scheme, second order accurate ya, untuk mencari turunan kedua. Langsung kita masukkan di sini, kita substitusikan, otomatis nanti menjadi persamaan linier ya, karena semua nanti jadi linier, tidak ada turunan lagi. Nah, sehingga di sini ini menjadi persamaan ini yang kita bisa lihat bahwa kalau kita ingin mencari nilai di satu titik IJ, maka nilai di titik IJ ini akan tergantung pada nilai neighboring point. Nilai poin-poin yang ada di sebelahnya atau poin tetangga ya. Jadi poin-poin yang ada di sekitarnya. Atau dengan kata lain kalau dibalik, misalkan ada perubahan di nilai di salah satu poin ini, maka ini akan mempengaruhi nilai di poin-poin yang lain ya, karena saling tergantung. Ya, nilai satu titik tergantung pada nilai-nilai yang lain. Nah, ini pengertian ya dari persamaan eliptik ya, klasifikasi persamaan eliptik. Ya, sehingga di sini nanti ya, kalau kita katakanlah kita punya berapa poin, misalkan di sini ya, katakanlah kita punya 10 ke arah X dan 10 poin ke arah Y misalkan, maka nanti total ada 100 poin misalkan. Nah, nanti mungkin ada boundary dan sebagainya ya. Nah, nanti akan berarti ada kurang lebih berapa? Maksimum ada 100 poin begitu ya. Ada 100 persamaan, misalkan seperti itu. Nanti dikurangi dengan boundary condition. Ya, jadi artinya kita akan mencari apa? Nilai-nilai yang tidak diketahui dengan mengaplikasikan cara di sini. Sehingga kita punya persamaan linear, dan kalau kita selesaikan secara simultan untuk semua titik yang tidak diketahui, maka kita akan punya set persamaan linear. Nanti tinggal dibuat koefisiennya ini. Ya. Jadi persamaan ini berlaku untuk semua interior point ya. Jadi kalau udah ada boundary nanti tinggal dikurangkan dengan boundary-nya jumlah persamaannya. Baik, nah sekarang kita akan lihat ke contoh soal di sini ya. Ya, kita lihat ke contoh soal. Here we have example 2, 29.1 in the book, yeah, in which we have a plate, yeah, and we want to find the temperature, the steady state temperature. So we have a point here, a note here, which is steady state, yeah. So it's not the function of time. And we need to find the temperature, the distribution of temperature for all points, at all points of a heated sheet of metal. The edges of the sheet are kept constant temperature. Yeah. So we see here that we have a boundary condition here. On the top side, we have 100 degrees Celsius. And on the left side here, we have 75 degrees Celsius. And on the right side, we have 50 degrees Celsius. At the bottom, we have 0 degrees Celsius. So that we need to find the distributions on the plate. And now we want to make a grid in which the sheet is divided to 5 by 5 grids. Okay, so that we have here, we divide into 5 grids. Yeah. So we divide the domain, the sheet, into 5 by 5 grids. Yeah. So that here we will have this illustration of the grid points. Yeah. So actually we have 5. So that here we have 5. So 1, 2, 3, 4, 5. Yeah. So each of the point here we have.
Mohon maaf Bu Vivin, suaranya kurang jelas.
Masih kurang jelas ya?
Udah Bu, sampun.
Kecil Bu suaranya.
Kenapa?
Suaranya terlalu kecil Bu.
Kecil.
Jauh iya, terlalu jauh.
Ya, kalau gini sudah lebih jelas apa enggak ya?
Sudah Bu.
Jelas Bu.
Okay, yeah. Okay, so we will divide into 5 by 5 grids, yeah. So that we have here 5 by 5 grids, yeah. So actually we start from the boundary as well, yeah. So we have 1, 2, 3, 4, 5, and then again to the vertical direction as well. We will divide into 5, yeah. So that we will divide into 5 points as well. So 1, 2. Here we have 3, 4, and 5. So actually we have 5 by 5, but we will not solve all of them because some points are the boundary points, so that we don't have to calculate it. So for example, here we have points here, so that will be the boundary points, so that we have the temperature already, so this will be 75. As well in this point, it will be 75. While here in this point, we have 0 degrees Celsius. So here we have the boundary nodes. And here we have 50 degrees. So we don't have to calculate it. Yeah, we don't have to calculate it. Yeah. So here we have 50. And this one is also 50 degrees Celsius. And here we have 100. Yeah. So if we want to find the distribution, so that will be the interior points in which we don't know the value. Yeah. So here we have 9 by 9, yeah, 9 by 9 points in which we, 3 by 3, which is a total of 9 points in which we have to find the temperature. So this is unknown, yeah, temperature. We have 9 unknown temperature. So that we will find the equation for each of the unknowns here, yeah. So that, for example, we want to find the temperature here at I1 and J1. So that if we want to find the temperature here, it will depend on the temperature of the point on the left, on the right, the top, and the bottom. Again, if we want to solve for this one point, so that will depend on the point on the left, the right, the top, and the bottom, and so on. Yeah. Again, if we want to calculate here, so it will depend on the temperature on the left, on the right, on the top, and on the bottom. So that we have a total of 9 equations to solve for the 9 unknown temperature. Ya, jadi kita akan mencari 9 persamaan, yaitu yang tidak diketahui temperaturnya. Kalau pada bender ini sudah tidak perlu dicari ya, karena memang temperaturnya sudah tahu kita. Ya, kita tetapkan bahwa temperaturnya tertentu. Berarti yang perlu kita cari hanya yang tidak diketahui temperaturnya. So how can we apply this one? Now, before we continue, we have 2 types of boundary conditions. So before we continue on the discussion, I want you to know that we have 2 types of different boundary conditions. So the first one is called the Dirichlet boundary conditions, and the second is called the Newman boundary conditions. So if we have the Dirichlet boundary conditions, it means that if we have a function u as a function of x and y, so that if we have a Dirichlet boundary condition, it means that we have a boundary condition in which u is known to a constant value. For example, u equals to 75. Or the temperature, the unknown value here, the dependent variable is equal to 75. The temperature here will be equal to 50. The temperature here will be equal to 100. So this is an example of the Dirichlet boundary condition. Well, we can also have the second type of boundary condition in which the known value is not the unknown, the temperature directly, but instead we have the gradient of the dependent variable. So what we know is the the gradient of the dependent variable. So that, for example, we have the du over dx is constant. So what we have here is the gradient. So this is another type of boundary condition. But now we will talk about Dirichlet first in this example, in which the unknown value is here is defined as the temperature directly. So explicitly the temperature is known. So that here we will find the equation or the balance for node 1. Yeah. So that if we have before, yeah, from these calculations is that if we have delta x equals to delta y, so that we have ti plus 1j plus ti minus 1j, so the node on the right plus the node on the left plus the node on the top plus the node in the bottom minus for the point itself. So that here, for example, we want to find T11, so that we can write down the equation for T11, so that will be equals to the temperature on the left, yeah, 75, plus the temperature on the right, which is T21, plus the temperature of the top, which is T12, plus the temperature at the bottom, which is 0, minus 4 times the point itself. So T11. So that will be equals to 0. So that if we want to find that, yeah, so find this value, so that it will depend on the value on the node on the top and on the right. And the other are the boundary value. So that we can write it down here, yeah, T11, yeah, so that will depend on T21 plus T01 plus T12 plus T10 minus 4 T11 equals to 0. With the boundary temperature known here for T01 and T10, so that now we have minus 4 T11 plus T12 plus T21, that will be equal to 0. So we have one equation, yeah, for the first point. And we need to define for all of the other points here, so that we will have a total of 9 equations. Yeah, so this is an example. Yeah. So this is the points, the boundary points, and this is what we need to find. Yeah. So here we start from the top left. Yeah, top left. So T13. So that will be equals to T03 plus T14. Wait, T14 on the top plus T12 on the bottom plus T23 on the right. So the neighboring points minus 4 times T13. That will be equal to 0, so that we can insert the boundary points, the boundary value 75 and 100, so that we will have here another equation. So we do for the same for the rest. Yeah. Now we go on the top midpoints. Yeah, top midpoints. We have T13 plus T24 plus T33 plus T22 minus 4 T23, the point itself. And we have a boundary point here, which is 100, so we insert that. So we have the second equations and so on. So that when we want to construct the coefficient matrix of A times the unknown T, that will be equal to the right-hand side. So we can see here the pattern. So that we have 4 here. Yeah, so this will be similar. We can multiply it with minus 1. So that will be positive 4 and that will be minus 1. So that we have this sort of matrix. We have a sparse matrix in which we have banded matrix. So if we see here, so this is the dependency, the coefficient for the point itself that we want to find, Tij. And then here is the dependency to the point on the right. So that is T, the coefficient for Ti plus 1j. And this is the point on the top. So Ti j plus 1. So this is the coefficient of the node on the top. While on the left here we have Ti minus 1j. Yeah. And again here we have Ti j minus 1. So this is the coefficient for the node on the bottom. So we have a pattern here. Yeah. So we have a pattern such as, what if we have a three-dimensional problem? Yeah, if we have a three-dimensional problem, so that we will have another 2 points there. Yeah. So for three-dimensional problem, we will have another one there and another one there, which relates to the position of the south and north. Yeah. So if we talk about three dimensions, so then it will be E, J, and K. So that will be at K plus 1, and the dependency to the node at K minus 1. So we can see a pattern here, which is a diagonal pattern. We have a bandwidth here. So this, later we can solve the system using the method that we have learned before in part 4. Yeah. Right. And we can see here on the right side here, we have the right hand side, which is appears in the equation, which comes from the boundary value. Yeah, so we see here that this boundary value will be moved to the right hand side as a constant there. So that will be the right hand side. So we can see here that if we have a different boundary condition, we have different boundary value, so that will have different right hand side. Yeah. Ya, jadi kita bisa selesaikan persamaan yang sudah kita buat di sini dalam bentuk matriks semacam ini ya. Bisa dengan Gaussian elimination, bisa dengan Gauss-Seidel atau metode iteratif yang lain ya. Jadi kita bisa lihat di sini ya, apa yang kita pelajari yang lalu itu memang saling terkait ya untuk menyelesaikan problem yang lebih kompleks. Baik. Ya, ini kira-kira ilustrasinya semacam ini ya. We can also write it down as this one if we want to, for example, solve it using iterative method, yeah, so that we can find, for example, in iterative method, so that we can find here, for example, from the first equation, so that we have T11. So we move all the value on to the right. So we have 75 plus T21 plus T12 over 4. And then we can get the second equation here. Yeah, so T21, that will be equals to 0 plus T13 plus T11 plus T22 over 4 and so on. So that we have a set of equations that can be solved using iterative method. Oke, any questions? Mungkin ada pertanyaan, silakan.
Bu mau tanya.
Iya, silakan.
Itu kan tadi kan sebelumnya dari Laplace equation kemudian jadi linear equation. Nah,
Ya,
itu kan kalau di buku perpan itu kan langsung ada tabel gitu Bu. Tabel linear equation-nya. Jadi nggak tanpa Laplace-nya. Nah,
ya.
nanti untuk project itu apakah kita boleh langsung pakai yang masukin linear equation atau harus nurunin dari yang Laplace equation?
Iya. Jadi memang kalau di buku heat transfer ya, dalam buku heat transfer, dalam buku perpan, itu memang langsung muncul. Kenapa? Karena itu adalah domainnya metode numerik, sehingga tidak dibahas di perpan, begitu ya. Jadi kenapa di perpan hanya ada tabel, langsung ada nilainya berapa, itu tanpa tahu dasarnya apa kok jadi seperti itu ya. Jadi persamaan ini. Nah, yang kita pelajari di sini justru yang tidak muncul di perpan itu ya. Jadi ini kita menjelaskan kenapa di perpan tiba-tiba muncul nilai semacam itu. Jadi disinilah part dari metode numerik ya. Itu pentingnya metode numerik ya, digunakan di yang lain. Sehingga di sini bukan kita belajar perpannya, ya, tetapi kita belajar bagaimana mentransformasi ya, dari persamaan heat conduction sehingga menjadi persamaan set linear. Sehingga itu justru pentingnya metode numerik ya. Jadi kalau langsung diambil dari heat transfer kita nggak tahu prosesnya, ya.
Iya. Makasih Bu.
Ya. Jadi justru nantinya yang saya harapkan itu diuraikan ya. Jadi kalau kita punya suatu persamaan begitu ya, semacam ini kalau di transfer mungkin tiba-tiba kita punya node di interior node rumusnya ini, di boundary node dengan heat flux misalkan. Di boundary node dengan heat flux misalkan nilainya perumusan yang dipakai ini misalkan. Nah, itu justru kita ingin belajar bagaimana kita mengkonstruksi persamaan ini. Ya, artinya nanti dituliskan misalkan saya punya 9 titik ya. Ya, misalkan semacam ini. Maaf. Ya. Maka tuliskan node 1, 2, 3, 4, 5, 6, 7, 8, 9 perumusannya bagaimana. Node pojok misalkan ya, kalau ini misalkan temperatur tidak diketahui, ingin kita cari. Ini masukkan persamaannya. Gitu ya. Bagaimana cara menurunkannya. Termasuk juga di boundary misalkan. Misalkan temperatur boundary tidak diketahui tapi yang diketahui adalah heat flux. Nah, itu gimana cara mencarinya kok bisa dapat persamaan seperti itu. Ya, jadi itu justru di sini poin kita adalah menurunkan ya dari persamaan sini menjadi ini. Baru kemudian setelah itu menggunakan cara-cara set persamaan linear aljabar yang sudah kita pelajari sebelumnya. Kalau di perpan langsung menggunakan Gauss-Seidel ya seperti itu buku perpan. Nah tapi sebetulnya tidak terbatas Gauss-Seidel ya, kita bisa menggunakan yang lain. Sekarang kita sudah tahu bahwa kita bisa menyelesaikan menggunakan cara-cara yang lain. Ya mungkin itu penjelasannya. Okay, so there is a question about the method in heat transfer in which we directly have a point and then we have the equations directly in linear equations. So the point here is that we need to define define how this equation comes from. Yeah, we need to derive it. Yeah, by substituting the central divided scheme that we have learned before. Baik, mungkin ada pertanyaan lain sebelum saya lanjutkan, silakan. Ya, silakan, mungkin Kian.
Izin Bu, ini kan tadi di contohnya itu untuk shape yang kotak ya Bu ya. Kalau seumpama shape-nya itu tidak kotak, itu cara menghitung pojoknya bagaimana ya Bu? Cara menghitung titiknya yang tidak kotak itu.
Ya, nah nanti tergantung pada bentuk ya. Jadi kalau tidak kotak bagaimana? Nanti tergantung pada bentuknya. Nah nanti itu bisa dilihat di buku ya. Jadi bisa dilihat di buku. Nanti ada. Nanti sebelumnya ini kita akan coba bahas dulu ya. Nanti setelah ini kita akan lanjutkan ke sana untuk bentuk yang sedikit berbeda ya.
Ya, terima kasih Bu.
Baik, mungkin ada pertanyaan lain terkait dengan cara diskritisasi. Baik, kalau tidak ada, kita lanjutkan di sini. Ya, di mana di sini kita punya secondary variable. Seperti tadi, katakanlah tadinya yang kita bahas tadi itu kan boundary condition saya sebutkan ada dua macam. So there is two boundary condition as I mentioned before that we can have the verified boundary conditions or we can have the Newman boundary condition in which not the unknown is explicitly known but is the gradient which is known. So that when we talk about gradient means that we talk about flux, so that we will talk about the secondary variables here. Yeah. We'll talk about the secondary variables here in which form the heat conduction case, yeah, or the heat equation case. This will be similar to the heat flux. Yeah. So if we recall what we have learned in heat transfer, that we can find the heat flux in x direction, so that here we have qx, so that is in q in x direction, so heat flux in x directions, or yeah, so that we can write it down as minus k accent, which is the heat conduction, times the gradient. And the gradient here is in x direction, so that will be ti plus 1j minus ti minus 1j over 2 times delta x. So that if we have qx, so that is actually minus k accent times dt over dx. Yeah. Or because we have dd, so that will be del t over del x. Again, if we have qy, so that will be minus k accent del t over del y. So the first derivative. So we substitute the first derivative where ti plus 1j, the first derivative in x direction, so ti plus 1j minus ti minus 1j over 2 delta x. And that we also, so that we can also, it should be y, so we can also find q in y direction, so that will be minus k accent del t over del y, so that will be t j plus 1 minus ti j minus 1 over the distance, which is 2 times delta y. And that, so the resultant, the magnitude of the heat flux, yeah, the magnitude of the heat flux will be equals to the square root of squared qx plus squared qy. So this will be the magnitude of the total heat transfer at a point. And we can find the gradient, the direction here. So beta here will be the arcus tangent of qy over qx. So this is relates to the secondary variable. Yeah. So that, for example, if we have q value, yeah, we have q value, so that we can find the dependency here. So that we can insert, for example, we have a boundary condition in which we need ti plus 1, so we can substitute ti plus 1 minus it. We can change that so that to include the heat flux. Yeah, so we see here that, for example, we want to apply the Newman boundary condition, okay, in which, for example, here, so here, for example, we don't have the boundary points here on the left here. It's not the Dirichlet, but instead we have the Newman. So what we have here is dTTx value. Yeah. So for example, we don't know the temperature explicitly, but we have dTTx value. So what happened here? Here, for example, this is a boundary node. Yeah, the boundary node. So that here, to apply the Newman boundary condition. So for example, we want to calculate the point at t0j, yeah, because we don't know this point, we don't know the value. Yeah, for example, what we have is the gradient here. So this is the Newman boundary condition, Newman. So that if we have a Newman boundary condition, it means that we still need to find the temperature at the boundary. Yeah, we still need to find the temperature of the boundary because we don't know the temperature yet. What we have is only the gradient. So that how to find for the value at the boundary points. Yeah, so if we have Newton boundary conditions, so the calculations for the boundary points can be calculated with this with this equation. So if we want to find the value here, so that will be equals to Tij plus Tij plus Ti minus j, so the point on the left. But if we look at the domain, we don't have the point on the left. Yeah. So this is the boundary point. So what is this called? So we make an imaginary point here, which is called the ghost point. So this is called the ghost point because it's not really existing, but we make an imaginary point. So actually the domain is on there. So we don't have this calculated, but we make an imaginary point, which is called the ghost point, to help with the calculation. So that here, when we want to calculate this one at T0j, so that will be equals to Tij plus T minus ij, the point on the right plus the point on the left plus the point on the top plus the point at the bottom minus 4 times the point itself. And that will be equal to 0. So actually this is the same as the other interior points. But the difference is that now, because you don't have the real points on the left, so that we make an imaginary point, which is called the ghost point. So that now we try to apply the value that we have as a boundary condition here. So what we have here is the Newman boundary conditions. So the Newman boundary condition is the value that we have here is the gradient. So the gradient here is approximately equal to Tij minus Ti1j over 2 delta x. So what is the approach that we use here? So this is also the central difference approach. So that the gradient at this point will be equals to the value on the right minus the value on the left over the distance, which is 2 delta x. So that if we have this value known as a constant value, so that now we can substitute to find the ghost point. So this is the ghost point, so that we can rearrange the equations to get the value of the temperature at the ghost point. So the temperature will be Ti, yeah. So if we move that to the left side, so this goes up, yeah, 2 delta x times the gradient here, minus move that to the left and that one to the right. So Tij will be equals to Tij minus 2 times delta x times the gradient, the boundary condition which is known, which is del T over dx equals to constant, which is known. So that if we know this value as a boundary, so that we can substitute Tij there with T minus ij, which is the ghost point here, with this value. So that if we substitute it here, so that we have Tij and Tij. So that becomes 2 Tij minus 2 delta x times the gradient plus T0j plus 1, similar to before, plus Toj minus 1, this point at the bottom, minus 4 times the point itself. So this is the final equations that we have for the boundary points if we have the Newman boundary condition. Yeah. So that will be 2 times of Tij, so 2 times of Tij minus 2 times delta x times the gradient which is known at that point, plus the point at the top plus the point at the bottom minus 4 times T0j. The same apply if we have 2-dimension problem in y direction. So for example, here we have that is known value
And we want to calculate it here. For example, the domain is going up there, so that we create a cosine point here, a cos point. We create a cos point so that the calculation here, for example, this is Tij, this is Ti minus 1j, Ti plus 1j, and that will be Tij plus 1. So that the final equation will be 2 times of the point here, because we don't have that point. So 2 times Tij plus 1 minus 2 delta y times the gradient del t over del y plus the point on the left, on the right, yeah, so ti minus 1j plus ti plus 1j minus the point itself for tij will be equals to 0. Yeah, so this is for the bottom boundary. Yeah. So here we have the Newman boundary condition at the bottom. Now this one on the left. And again, the same we can apply for the top and on the right. So that if we have this sort of problem, yeah, in which we have the mixed problem, so this is in the book, problem 29.8, in which we have the top boundary is the Dirichlet boundary, in which the temperature is known for each of the points. So this is 0, 25, 50, 75, and 100. And again, on the right, we have the precise, the explicit temperature already, while the left and the bottom here is insulated. So do you still remember insulated, what is meant by insulated? And we have the term insulated, so it means that what is meant by insulated? Insulated means that there is no heat flux across. So that means this Qx will be equals to 0 and Qy equals to 0. Or we can say that del T over del X equals to 0, or del T over del Y equals to 0. So if you look at here in the equations, because Q here is 0, so that means this is 0 as well. So the gradient here is 0. And if the gradient here is 0, it means that this will be omitted from the equations. So if we have the insulated case, yeah, insulated case, there is no heat transfer across. So that means dt dx over is equal to 0. So that we have the equation will be 2tij plus t0j plus 1 plus t0j minus 1 minus 4 t0j will be equals to 0. So that with this, we can calculate that at this point, yeah, for example, so that t, for example, 0, 1, 2, 2, yeah, this is t01, and this is t03, and this t04, so that we have t 2 times of t04 plus t01 plus t03 minus 4 times t02, that will be equal to 0. Okay, so that we have the bottom boundary here, yeah, and this is insulated as well, so we can apply the same. So this is this will be T10, yeah, and that will be T20, and that will be T30, and that will be T21. So that if we want to calculate, to find the equation here, yeah, at this point, so that we will have 2 times 2 T21 plus T10 plus T30 minus 4 times T20, that will be equals to 0. Okay, so this is the example. So that here, for this case, we need to solve for 1, 2, 3, 4, yeah. And in y direction, we have 4 as well. So a total of 16 points, 16 unknown points. And that means we need to have 16 equations, yeah, 16 equations to solve for the unknown here. Okay, so that with this case, we have we can imagine that we will have 16 equations. So if we construct a matrix, so that will be 16 by 16 coefficient, yeah, a matrix which is have 16 by 16 element. Yeah, so the matrix size will be 16 by 16. If we have 100 nodes, yeah, if we have 100 nodes, it means that we have a matrix of 100 by 100. Yeah. If we have 1 million nodes, for example, which is appear in most of the computational methods, yeah, for example, in CFD or finite element methods, for example, millions of nodes, yeah, so that we will have a matrix which is millions by millions, yeah. So that means we will have millions equations to solve for millions unknowns. So we can imagine the size of the problem, yeah. So that with large size, very, very large size problem with many nodes, it's not efficient to construct the matrix explicitly, because we will end up with very large matrix in which actually the matrix is only filled in the diagonal, yeah. So we have the field only in diagonal, yeah, for example, like this one, while the number of the size of the matrix is fairly large. So actually it's very sparse matrix. So in this case, it will be preferable to use an iterative method, because we don't need to construct the matrix explicitly. Okay, so is there any question?
Bu, mungkin saya tadi tidak mengikuti karena sinyal yang itu Bu, yang parabola 29,8.
Yang mana itu?
Itu kenapa dia 0,4 Bu? Kenapa enggak T 1,2 gitu Bu?
Yang mana ini?
Iya,
ini?
Iya Bu, iya Bu. Iya, yang T 0,4 itu Bu.
Ini ya, jadi ini tadi kenapa kok 2 kali T04?
Iya betul Bu. Kenapa dia bukan 2T 2,2 gitu Bu? 1,2.
1,2. Maaf, iya benar ya. Ini salah ya, salah nama ya. Betul. Ya, ini seharusnya, ya betul. Ini bukan T0,4 ya, salah. Ini T1,2 karena posisinya adalah pada 1 ya. Jadi 1,2 betul. Ya ini koreksi ya, terima kasih. Jadi bukan T04 ya. Ini tadi karena ngikutin 0, 1, 2, 3, 4 ya. Jadi ini seharusnya pada posisi I-nya. Ini kan I0, ini I1 ya. J-nya ini J0, J1, ini J2. Jadi seharusnya betul T12 ya. Harusnya T12. T12 ya. Jadi 2 kali T12 ditambah T01 ditambah T03 dikurangi dengan 4 T02. Ya, betul. Ya, terima kasih. Yeah, so there's a correction. Yeah, so for the indexing, it's not
correct before. Yeah, so this should be T12. So the indexing should be at I1 and J equals to 2. Yeah. Okay, so this is for solving partial differential equations. For in this case, we discuss in chapter 29 is about the elliptic problem. Yeah, elliptic problem. Okay, and relates to the question before. Relates to the question before. I would like to open the book. Yeah, so there's a question before about what if we have a point which is not exactly in it's not exactly as the shape of square, is it the question? Yeah, what if we have different shape? Yeah, what if we have different shape? And we can see that in the book. Yeah, so we will open the book at part 8, that is at chapter 29. Now yeah, we will look at a boundary condition problem. Yeah, so you can open it in the book as well. Yeah, so if we open the book, yeah, if we open the book and we go on to page 860, which is about the boundary condition. Yeah, we have discussed about the boundary condition before. We can have the required boundary condition or the Newman boundary condition, and we have discussed how to use the Newman boundary condition. Now we can also apply for different boundary shape. So you can look at in subsection 29.3.2, in which we can have the irregular boundary. Yeah, in which we have the irregular boundary. So that here, for example, we have a system here. Yeah, in which we have a non-rectangular boundary. For example, here in the case we have here, yeah, a boundary which is following a curvature. Yeah, and this is commonly encountered in a real problem. Yeah, for example, we have a cylinder. Yeah, and so that cylinder will not have a rectangular contour. Yeah, but it will instead it will have a curvature here. So that how can we calculate this one? So if we apply the note here, we make a discretization with the grid point here, so that we will see that the distance between the grid will not be uniform. Yeah. Distance between the grid will not be uniform because the grid should fall into the boundary line here. Yeah. Should fall into the boundary line. So that if we have a non-irregular shape, yeah, like this one, so that the distance here in x direction here will not be the same to the other grid distance. Yeah, so if we have here, for example, the first to the second node here, the other points have delta x, so here we can have alpha 1 delta x, so we multiplied the delta x, the regular delta x as the other with a coefficient of alpha 1. So it means that the grid spacing is not the same. So that here, if for example, we have the spacing to the left here is alpha 1 delta x, and the next spacing here is alpha 2 delta x. And again, in y direction, we apply the same now. The distance here is multiplied by beta 1 and beta 2, yeah, for the second grid. So that now we will have this sort of calculation, yeah, so that we have to insert the real value for the delta x. So not we cannot assume that delta x is uniform, but now we have to insert the true value of delta x. So it's if the true value is alpha 1 delta x, so that we divide it with alpha 1 delta x. So that delta del t over del x at I minus 1i, yeah. So at I minus 1i, so that can be approximated, yeah, is equal, approximately equals to gi j minus ti minus 1j over alpha 1 delta x. So if you look at these equations, what is the differentiation scheme that is used here? You still remember? Do you still remember what kind of differentiation is used here?
Apa ya?
Skema diskriptasinya apa kira-kira? Kalau kita lihat semacam ini?
Formulasi.
Ya,
Backward scheme.
backward, betul, backward.
Backward.
Ya, kemudian
Iya Bu, backward.
backward
Ini
scheme.
satu sama forwardnya di sini.
Iya, jadi kalau kita perhatikan di sini ada backward dan forward, ya, ada backward dan forward, ya. Jadi kalau kita perhatikan di sini, so if we look at here, for example, we have a point of I plus 1 and I minus 1 here. So the gradient at I minus 1 here, at I minus 1, so the gradient here is approximated by Tij minus Ti minus 1j over the distance. So if we look at here, for example, we have here, so the gradient here is approximated like this one. So this is a forward scheme, yeah. So this is a forward scheme. Yeah, forward scheme. So we find the gradient based on the value, the point after, yeah, because the gradient is want to find at this point, so that we need to find the gradient based on the point after minus the point itself over the distance. So the distance will be alpha 1 delta x. And the second, we want to find the gradient at I plus 1. So I plus 1 is here, for example. So if we want to find the gradient at I plus 1, this will be approximated by Ti plus 1 minus Tij over alpha 2 delta x. So that will be a backward approach. Yeah, so this one is a backward approach, backward scheme. Now wait for one. So that this is the scheme that we can apply, yeah, as the gradient, so that later we can find, yeah, if we want to find the second derivatives, yeah, so that if we want to find the second derivative, so that this will be calculated by del over del x dt over del x, so that we insert the value here of del x I plus 1 at I plus 1 minus del t over del x I minus 1, yeah, over the distance, which is average. So alpha 1 delta x plus alpha 2 delta x over 2.
So that we rearrange the equation, we move that up and so on. Yeah, we do the rearranging the equations so that, yeah, solving it mathematically. Yeah, we try to uh, uh, rearrange this. Yeah, so that we have only one division only. Yeah, here, so that here we have the final, yeah, equations here, in which we can calculate it with 2 over delta x squared delta x multiplied by ti minus 1j minus tij over alpha 1 times alpha 1 plus alpha 2 plus ti plus 1j minus tij over alpha 2 times alpha 1 plus alpha 2 plus, now this is in y direction. Yeah, so if we do the calculation, we substitute in x and y in the Laplace equation, so that will be delta squared t over del x squared plus del squared t over del y squared equals to 0. So this is t del squared t over dy squared here, and that will be equals to 0. So that if we insert the value of alpha and beta here, so that we have a coefficient, so that we can later collect together Tij with Tij, so that again, the value of Tij will depend on the value of Ti minus 1, Ti plus 1, Tij minus 1, and Tij plus 1. So that if we want to find the value here, yeah, so that will be similar. Yeah, that will be depends on the left, on the top, on the right, and the bottom, and minus the coefficient times the point itself, but it's not 1. The coefficient is not 1, but we need to insert the value of alpha and beta here. Yeah. Okay, so that then with that we can construct the equation for the points, the interior points, which is close to an irregular boundary. Yeah. Okay, so that you can read along in that. Yeah, so you can see here that at the boundary here, the coefficient will be a little bit different, yeah, compared to the other interior points. So we see here that this point here, T11 here, has different coefficient because it's close, is the interior points which is close to the irregular boundary. Okay, so I think, yeah, that is for the explanation. If we have a non-regular boundary, yeah, and that will also applies if we have irregular grid spacing. Yeah, so if, for example, we have irregular grid spacing, we can apply that one as well. Yeah. And you can read along with that, yeah, with that in the book as well. What if the boundary curve here has don't have a derivative boundary condition, but we have a normal gradient which is specified at the boundary. So this one we need to make another, yeah, another calculation, yeah, another calculation here, yeah, because we have normal normal boundary condition specified, yeah, instead of the derivative. Okay, so that will be yeah, about the elliptic equations. Any other question?
Ya, saya izin bertanya, Bu.
Ya.
Tadi yang irregular itu berarti yang pakai alfa beta itu hanya di shape yang tidak kotak ya, Bu ya. Berarti untuk yang seterusnya, node seterusnya itu dihitung dengan Laplace sebelumnya itu. Apa benar atau bagaimana?
Ya, jadi kalau yang di lain ya, jadi itu hanya berlaku untuk yang di sini saja. Mana tadi ya gambarnya ya, diskritisasinya. Nah ini, ya ini hanya berlaku di perhitungan interior point ini saja. Kalau yang lain bagaimana? Yang lain sama, karena ini ya misalkan di sini, ini kan tergantung pada kiri, kanan, atas, bawah. Nah ini sudah jaraknya sudah sama, delta x semua sudah uniform begitu ya. Jadi kalau sudah uniform,
ya jaraknya sudah sama delta X delta Y-nya, maka ini menggunakan persamaan biasa. Ya, jadi yang berbeda hanya di sini saja. Ya, begitu.
Lagi Bu, untuk alfa sama beta itu apa ditentukan nanti Bu nilainya?
Iya Bu, ya ditentukan. Jadi bagaimana nilai alfa dan beta? Kalau dalam kasus ini ya kebetulan ini kan sama ya. Jadi ini alfa 2-nya sama dengan 1, beta 2-nya sama dengan 1. Kalau dilihat dari kasus ini kan hanya beta 1 dan alfa 1 saja yang berbeda ya. Nah, nanti bagaimana kita menentukan? Nah, baiknya itu dibuat berdasarkan dimensinya ya. Jadi memang berdasarkan dimensi kita seperti apa, nanti kita bisa ukur jaraknya. Jarak dari busur itu ke titik berapa.
Baik, terima kasih Bu.
Ya. Jadi kalau kita punya problem sendiri, if we have a problem, so that we need to find the distance of the curvature first, ya. Yeah. So that if we have the distance, so that we can define alpha 1. Yeah. So it should be defined. Yeah. It should be defined from the geometry of the domain. Ya, jadi mungkin kira-kira begitu ya. Yeah, so that the project will relate to this. Yeah, will relate to this. It will be presented on week 13, 14, and 15. So now it's week 11. Yeah, week 11. So we have another 2 weeks to prepare for the project. Yeah, another 2 weeks. So that the project will be all of the report should be submitted in week 13. Yeah. All of the reports should be submitted on week 13, but then for the presentation, we will have a list of presentation, yeah, so that will be in 3 weeks, so week 13, 14, and 15. But all the reports should be handed in, should be uploaded on week 13, so that we have a fair marking for that. Yeah, so all of the projects should be uploaded in week 13. And it is an open problem. Yeah. Inshallah next week I will give a guideline for the report. So what should be included in the report? Yeah, what should be included in the report? First, there should be a brief explanation of the problem description. So what is the problem description? What is the domain that we want to solve? Yeah, along with the illustration of the dimension. Yeah, the dimension with all the measurement, the length, and so on. Yeah, so the dimensions should be stated clearly, and also, yeah, the problem description includes about the domain, the dimension, and also the boundary condition that is used. Yeah, and then you have to continue with the discretization process. So how many grids that is used and how to transform the general equation. So you should put the general equations as well, the general equations. So that is the problem that arises from the engineering problem, from the theoretical background of engineering. So what is the equations to be solved? And then applying the boundary, and then applying the transformation using discretization scheme, yeah, applying the discretizations, and then you write down the discretization for the nodes, for example, interior nodes, the boundary nodes, and so on. Yeah, you give an explanation of how you end with you get the linear equations, and then afterwards, what are the solver that you use to solve the set of linear algebra. Yeah, so the explanation whether you are using the Gaussian elimination method or using Gauss-Seidel method and so on. And it will be a coding practice as well, so that you should attach the code. Yeah, you should attach the code. Yeah, in which you you solve this problem. Yeah? Attaching the code and give some results on it. So it can be, the results can be in the form of contour, for example. So for example, here if we solve for the temperature so that we can display the temperature, the contour of the temperature. And also, for example, we can plot the value. Yeah. So for example, you can plot the temperature distribution along the X value at some Y position, for example. Yeah. So it can be a contour or a plot, XY plot, for example, or other. Yeah. And the problem is not limited, so you can find any problems, yeah, and that problem should be a PDE problem, yeah, should be a partial differential equation. And we have 3 classifications before. Today we still discuss about the elliptic equations. Later we will discuss about the parabolic equations. So you can choose which one of the PDE that you want to as a project. Yeah, you can use either this problem, the elliptical problem, or you want to solve an engineering problem which falls into the parabolic problem. Yeah. Okay, so next week I will give you a guideline of the report. So what should be included in the report. But for now, you can start on finding problems. Yeah, thinking about what you want to discuss. Yeah, what you want to do for the project. Okay, any questions? Ya, jadi ada pertanyaan atau tidak terkait dengan project ya. Jadi memang sifatnya open case, bisa apa saja. Yang baru kita bahas hanya persamaan eliptik. Nanti kita akan bahas persamaan parabolik dan bisa silakan Anda bebas bisa pilih mau kasus parabolik atau eliptik silakan. Ya. Atau yang merupakan gabungan keduanya juga memungkinkan ya, bisa saja gabungan keduanya. Untuk kasus yang lebih kompleks misalkan. Jadi memang kasus-kasus kompleks itu kadang jatuhnya tidak hanya ya dia secara dominan mungkin dominan lebih eliptik atau dominan lebih parabolik, tapi bisa saja gabungan begitu ya. Nah, seperti itu. Nah, itu untuk kasus-kasus macam itu silakan Anda boleh lihat-lihat ya, cari-cari kira-kira apa. Di contoh soal di buku ini juga banyak sekali ya. Tapi harapan saya ya kalau bisa mencari sesuatu yang berbeda. Jadi agak apa? Ini ya agak kreatif gitu ya, jadi nggak ngambil dari buku, kalau bisa diambil dari ya dipikirkan kira-kira apa ya kasus-kasus yang menarik begitu. Nah, nanti untuk report akan saya posting di ini ya di Classroom apa saja yang harus dimasukkan di dalam report ya. Yang jelas ada tadi saya katakan ada problem deskripsi, jadi apa problemnya, ini kasus apa, persamaannya apa yang harus diselesaikan. Jadi kalau ini heat transfer harus ada persamaan heat conduction-nya. Kemudian setelah itu bagaimana diskritisasinya, berapa jumlah grid point-nya, ya berapa ini apa namanya, bagaimana cara diskritisasinya, pakai skema central divided difference kah, atau pakai backward atau forward ya, seperti tadi ini ada yang forward backward tadi contohnya. Nah, kemudian penjelasan bagaimana dari transformasinya ya, dari persamaan PDE berubah menjadi persamaan aljabar. Artinya di situ harus dijabarkan untuk interior point, kira-kira rumusnya bagaimana, untuk boundary points rumusnya bagaimana, kalau ada boundary yang tidak sama atau ada grid spacing yang tidak sama katakanlah, nah itu bagaimana perumusannya ya, itu harus ada penurunannya. Jadi tidak ujuk-ujuk langsung jadi begitu ya. Tetapi ada prosesnya di situ. Karena ini tujuan kita adalah melihat proses ya. Nah, kemudian setelah jadi persamaannya, tuliskan dalam bentuk set persamaan, ini persamaannya yang diselesaikan ya. Jadi kalau misalkan saya buat 20 grid, nanti ada 20 persamaan, secara detail harus dijabarkan. Nah, kemudian setelah itu adalah ke metode penyelesaian set persamaan linear aljabar ya. Jadi apa yang dipakai? Apakah Gaussian elimination atau Gauss-Seidel atau LU atau yang lain? Ya, silakan di state, ya, harus jelas metodenya apa. Nah, kemudian setelah itu adalah hasil. Ya, hasil itu ditampilkan dalam bentuk, bisa dalam bentuk matriks data, ya, matriks data, atau bisa ya, kalau matriks data kan sulit melihatnya, ya, ada tampilan visual juga. Jadi ada tampilan visual, misalkan kontur atau plot, XY plot misalkan, ya. Misalkan saya mau mencari distribusi temperatur sepanjang sumbu X pada suatu nilai Y tertentu misalkan, itu juga bisa. Nah, itu nanti ada namanya post processing, ya. Jadi mengolah data hasil. Ya, setelah dari situ nanti kesimpulan. Dan ini adalah suatu open question, ya, suatu open case, jadi bebas problemnya apa. Yang jelas nanti originality, yaitu menjadi suatu poin, originality dari work. Nah, kemudian juga kompleksitas, ya, makin kompleks, misalkan ada yang mensimulasikan hanya segi 4 saja semua, ada yang dengan irregular boundary, otomatis nilainya berbeda, ya. Makin kompleks, nilainya akan makin kompleks dan benar, ya. Jadi tahapannya seperti itu, ya. Jadi harus benar, it should be accurate, ya, it should be correct, ya. And how complex is it? Yeah, a complex problem that have better marking. Ya, yeah. Jadi mungkin kira-kira itu. Ya. Jadi usahakan berhati-hati, ya, ketika menurunkan, mentransformasikan dari persamaan PDE menjadi linear, karena kadang ada kesalahan di situ. Proses transformasinya itu ada yang salah. Nah, itu mungkin yang perlu diperhatikan untuk project. Ya, jadi the project will due on week 13 for all of the group. Yeah. And then we will have the presentations. So there will be 18. So 6 for each of the week will present the result. So for the presentation, I want you to make a simple PowerPoint. Yeah, you can use other presentation file format. Yeah. But I need you to present the result so that your friend can also understand what you have been doing for the project. Jadi mungkin itu, ya, untuk projectnya. Jadi mungkin sudah punya bayangan, ya. Jadi sekarang kira-kira apa yang harus dikerjakan, gitu, ya. Silakan kalau ada pertanyaan. Okay. Is there any question? Tidak ada. Baik. Ya, sebelum saya akhiri, saya akan lanjutkan sedikit, ya, mengenai parabolik. Jadi ini supaya Anda punya bayangan saja, ya. Tidak akan kita bahas, tetapi tidak akan kita bahas saat ini semua, tapi paling tidak punya bayangan untuk project bahwa ada tipe yang lain, yaitu parabolik. Ya, ada tipe yang lain, yaitu parabolik. Okay, so we will discuss on chapter 30, which is about the parabolic equations. Yeah. So we have seen the first one. We have discussed of how to apply the numerical differentiation to substitute for the derivative that comes in the Laplace equations, that appear in the Laplace equations. Now we will talk about the second equations, which is the diffusion equations here. So this is included as a parabolic equation, as seen before. So here we have heat equations. If we have a parabolic equation, so that P squared minus 4AC should be equals to 0. So that here we have the heat equations, unsteady heat conduction. Yeah. For example, here we have a rod, and here the left one is ice, hold at a constant temperature, which is ice. So this is assumed to be 0 temperature. And on the right side, we have also a constant temperature, which is 0. So that we have a boundary value problem here. So the temperature, the boundary condition at the left at x equals to 0 is 0, and xx equals to 1, so that will be 0 as well. And the temperature the initial temperature, so this is the initial condition, at T0 is known that the distribution here following the sinus curve. So that if we have this heat equation problem, so that we will have a parabolic equation of B squared minus 4AC equals to 0. So that here we need...
Mohon maaf.
Iya.
Ini gambarnya tetap PDF buku tadi, Bu.
Oh, maaf ya, saya lupa share-nya. Pindah share-nya lupa. Ya, ya, makasih.
Iya.
Ya, sudah muncul ya?
Sudah, Bu.
Ya, maaf saya lupa tadi. Ya. So that if it, sorry for that. So we look at the parabolic equations now. So if we have a heat equation and we hold the boundary condition here as 0 on the left and on the right, and we have the initial condition at time equal to 0 here, it will follow sinus pi x. So it means that at initial state, the temperature is not constant here, but it is following the sinus distribution. So here, to solve for this problem, we need the boundary condition to have a unique solution. And here we have the boundary condition already. So how to solve using finite difference method? Now it's basically almost similar to what we have learned before in the Laplace equations. But now we have a function which depends on two independent variable, which is x in spatial direction x and t, which is in time, in time. So that now we can discretize as well the domain. Now the domain is x and t. We can discretize the domain into points as before. Now that if we talk about Tij, for example, so that represents the point, for example, here we have Tij, so that I here represented the x direction, while j here represented the time step, so that here we have slightly different variable for the y-axis. So now we have time direction in y. Okay, so that if we have the interval x with h and the interval t with k, so that is the time step. So here we can do similar to before. Now here, if we look at from the book, so the book is not using the indexing of I and J, but instead now it's using I and L. So in time derivative, in time here is using an indexing of L. So that if we have a point of IL here, IL, so that means the point at IL, will depends on the neighboring points as well. So we will look at the equation here. So this is heat conduction, in which we have minus del Q over del X, in which Q here is the heat flux. So the change of heat flux in this direction, that will be equals to rho C del T over del T. So this is capital T for temperature, small t is for time. So that if we want to, so that if we want to calculate, that should be del, so Q accent, Qi is equal to minus K rho C del T over del X. So this should be del X, It should be del X. So that we can change that to the, we can substitute there. We substitute it here. So that minus, so that will be K. Rho C, we can cross that with this one. So rho C is cross, so that we have K times the second derivatives of T in X directions. That will be equals to the first derivative of temperature in time. So this is the heat conduction equation. So that with here, with this one, so that we can apply, we can apply the discretization. Yeah, so we can apply the discretization. Now, to apply the discretization, we have to be careful because we have the discretization in x direction and we have the discretization in t direction. And this will not be the same as what we applied before in Laplace equations, because when we talk about time, it means that we have to define which time step. Is the calculation is based on the current time step or the time step after or other. Yeah. So that here we have two types of discretization. Yeah, so that here we have the heat conduction equation. So we have here K times the second derivatives in X. So this will be spatial discretization. So the spatial discretization will be the same as before. Yeah. So this is using the central difference in which this is calculated with Ti plus 1, the point after, the point after in x direction minus 2 times Ti plus Ti minus 1 over delta x, which is squared. And we have the temporal discretization in which this is the first derivative, and this first derivative is calculated by Ti at time step L plus 1, so it means that it's taken at this point, minus Ti at L, so that is the time step after, minus the time step before, over delta t. Yeah, so it means that if we want to calculate at this point, yeah, so that we can calculate from here, yeah, or the other way around. If we want to calculate this point, so that the time step after, yeah, so that will have the dependency to the point at the same location at the previous time step. While if we calculate the second derivative in x, so this value should be specified because this value taken at the current time step or the previous time step. So with the explicit method, if we want to use the first method, which is the explicit method, it means that all of the value here is taken from the known value. So it means that it's explicit because it's taken from the known value. So what is the known value? So it's here. So that when we calculated the second derivative, so it will be calculated with Ti plus 1 minus Ti plus Ti minus 1. And all of this value is taken at the known value, which is at the previous time step. Yeah. So that we can substitute this equation here and this one as well. So if we substitute this equation, so that we have this equation, yeah, and then we can find for the value at Ti and the subsequent time step, which is a new time step, which is L plus 1. So Ti at L plus 1 can be calculated by Ti at L plus lambda times Ti plus 1 at previous time step L minus 2 Ti at previous time step L plus Ti minus 1 at previous time step L. And the lambda value here is taken from here. So that will be K times delta T over square delta X. So this is the equations to find for the known value, the unknown value at the subsequent time step based on the calculation which is known from the previous time step. So if you see here that if we want to calculate this point, so that will depend on the point at that point and this neighboring point at the previous time step. So we see here that all of the value is already known because it's taken from the previous time step. Again, if you want to calculate at another point here at the next time step, so again, it will depend on the known points before. So this is called explicit. because here in the calculation, there is no need to do the iteration because all of the value is already known. So there is no need to construct a matrix and there's no need to do the iteration. We just need to calculate so that we have that already. So this is called the explicit method. Okay, so we will continue on the other methods next week, yeah, for the parabolic problem. But at least now you know that we can have a problem which is only as a variation in spatial direction in x and y, such as Laplace equation, or we can also have a problem in which we have a change in time, in which we have a change in time, so that means we have a parabolic equations. Or we can also have a problem which is a mix between the parabolic and elliptic equations. For example, we have two-dimensional plate, but we know that the temperature distribution on the plate can be unsteady. Yeah, so there can be a change of temperature distribution on the plate during time. So that means we have a mixed problem between parabolics and elliptic equations. So in that case, we have to combine these two methods. Okay, so this is to give you an overview of the project, so you can think of what of the project you want to solve, yeah. So you can discuss with your partner later, yeah, of the problem. Yeah. Okay. Baik, mungkin itu yang bisa saya sampaikan untuk hari ini ya. Jadi kita sudah punya bayangan di sini ada parabolik, ada eliptik. Bisa memilih salah satu ya, atau bisa bahkan gabungan keduanya. Karena ada kasus ya di mana kita memang menyelesaikan problem dua dimensi, katakanlah plat, begitu ya, temperatur pada plat. Ternyata temperatur pada plat itu juga distribusinya tidak konstan terhadap waktu ya. Jadi berubah juga distribusinya terhadap waktu. Nah, dalam kasus itu berarti gabungan ya, ada pengaruh waktu, ada pengaruh spasial baik ke arah X maupun Y, misalkan seperti itu. Nah, itu untuk problem yang lebih kompleks ya. Nah, arahannya kemana? Ya, arahannya nanti adalah ke metode penyelesaian yang lebih kompleks ya. Jadi ini memang digunakan sebagai basis dari finite element method ataupun CFD. Jadi basisnya dari sini. Oke, baik. Jadi mungkin itu yang bisa saya sampaikan hari ini. Mungkin kalau masih ada pertanyaan silakan. Baik, kalau tidak ada pertanyaan, saya rasa sudah cukup jelas untuk project ya. So for the project, it will due on week 13, yeah, due on week 13, and the group and the member has been uploaded in Classroom, so you can check in Classroom, download the file, yeah, for the grouping, so you know who is your partner, and you can start discussing with your partner of what you are going to solve for the project. Okay, so that will be the end of the class. Thank you. And Ahmed, are you here, Ahmed? Ahmed, are you here? Can you respond? Ahmed?
Ahmed balas lewat chat, Bu.
Oke, ada problem ya, nggak bisa. Oke, yeah. Alright, so there's a problem with the sound. Can you hear my voice? Okay. Yeah, you came late this morning. Yeah, please, please be on time, yeah, because we start from 7 already. Yeah. You will miss most of the important lecture today, yeah. So please, next time on time. Yeah. All right. So yeah, you can check with the project. Yeah, you have a group, so check it in Classroom. Yeah, make sure that you have a discussion. Yeah, and for the presentation later, I want you to each of the group member have have time to present the results. So not only one person who presenting, but each of the member of the group should present the result. Yeah, so there will be, you can take turns in presenting the slide. Yeah, but all of you should present the result. Yeah, so not only one of the member, but both of you should take turns to present the result. Okay, so I think that is for today. Thank you for joining the class. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih, Bu.
Ya, akhiri ya saya.